There's nothing better than meeting together and learning face to face about what's possible, and it's just great to be back together. And of course, a big shout out of thanks to Professor Narducci, has given generously of his time in extensive preparation for today's talk, taking him away because we all recognize that unlike spooky particles, Dr. Narducci could not be in two places at the same time. Professor, the floor is yours.
Thank you, Provost, for that wonderful introduction. A little bit daunting to see the large crowd, but I am up to the challenge that I think I faced today, where I bring you the excitement of the 2022 Nobel Prize, and in particular trying to explain the beauty and the mysteries of quantum mechanics to such a broad audience in 45 minutes. So let's get right to it. But first, just like Netflix, right before the movie that you want to watch, you have to watch a commercial. So I just want to highlight very quickly that particularly for those who are in Zoom land, but also those of you who are here, if you find some of the subjects that I'm talking about today interesting, let me highlight that the Office of the Secretary of Defense will be hosting a program review right here in Monterey on May 3rd and 4th, I believe it is. And we'll be doing a quantum tutorial to go with it the day or so before. So if you are interested, just reach out to me, I'll give you all the information. The Provost must have snuck a peek at my slides because he hit pretty much everything over here. I do want to thank the Provost for the invitation and Giovanna for the invitation here, all the IT who has been helping to put this together. Of course, the NPS Foundation for boosting my energy at the end of this lecture with some treats that I'm sure are coming. I also do want to highlight, though, I have been very fortunate in my career to receive funding to do some of this quantum work, which is I just find absolutely fascinating, from the Office of Naval Research and from the Army Research Office, as well as the Office of the Secretary of Defense. I am also very blessed to work in a fantastic department and in a fantastic campus where I can talk to colleagues both within the physics department and outside about all sorts of quantum stuff. And then I also want to highlight my colleague and lovely wife, Shihan Mimi, who's actually really the expert in quantum information, and she's the one that made sure that I didn't get anything wrong in the slide. So if it's wrong, it's my fault. Okay, so let me start off with the disclaimer. More than one of my colleagues have said, you know, those posters of you, they look great, but it looks like you won the Nobel Prize. So let me make a disclaimer. I did not win the Nobel Prize. I was not the runner-up. I was not the runner-up. I wasn't even close. Okay, so just to be clear, that was never in contention. And today's discussion about physics is going to be at the very superficial level. So the emphasis is really going to be on painting a coherent picture of the wacky world of quantum mechanics. And so I brought in some little, very rudimentary, very basic demos that I'd like to show. But as with every other analogy, you can only take it so far. So just keep that in mind. I think my talk is a little on the long side, so if you have a burning question, feel free to ask it. Otherwise, save it for the Q&A session. Okay, so when the Nobel Prize in 2022 was announced, I have to confess I was caught a little off guard. For some reason, I thought the announcement was coming the next day. So my students came into class, and what was I teaching that particular quarter? Happened to be teaching advanced quantum mechanics. And they said, what do you think about the Nobel Prize going for entanglement? And I said, wait, don't tell me anything. Knowing that it went for entanglement, I'm going to guess that it had to have been given to Alain Aspect, John Clauser, and Anton Zeilinger. Bam, yes. Now, I say that not to show you how smart or clairvoyant I am, because I'm neither, okay, but that's because this community has long recognized that this award was way overdue. And part of today's talk is to tell you exactly why we felt that way. So here is now, by now, famous caricatures of these characters. Here's a better picture of these gentlemen. And the Nobel Prize was given for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Now, in today's talk, I'm not really going to spend a lot of time talking about Anton Zeilinger's work. He has done a huge amount of just absolutely impressive experiments. But for the purposes of today's talk, I'm going to focus mostly on the work by Aspect and Clauser. And in particular, this phrase here, violation of Bell inequalities. And what does that mean? Now, I don't know about you. That sounds to me like something you might get punished for. Right? Oh, you violated Bell inequalities. Go home and, no dinner for you. So it doesn't sound like something you'd win the Nobel Prize. So let's see what this is all about. So let me start, and I will preface this by saying my physics colleagues probably can give this part of the lecture way better than I can. But let me start by saying, what's wrong with classical mechanics? And how did that lead to the advent of quantum mechanics and some of these really weird questions? So for example, Einstein had a debate. I will tell you a little bit about the famous Einstein board debate. And maybe this philosophical question, what is reality? Yes, that is something that we will ask in a physics class and in today's lecture. I will tell you about these Bell inequalities and what it means to violate a Bell inequality. And of course, then, this is the Naval Postgraduate School. And as we look around the room, of course, a lot of uniforms. What is it good for? Why does the Navy, why does DoD care about Bell inequalities? And so I will tell you a little bit about that. So let me start out by saying, okay, what's wrong with classical mechanics? What do I mean by classical mechanics in this context? Classical mechanics in this context is Newtonian mechanics. What did we learn from Sir Isaac Newton? F equals ma. And I have seen, actually written, that in the 18th and 19th century, it was believed that there were no more revolutions to be had in physics. We knew everything. Very dangerous attitude to take. But back then, they knew everything. Newton's equations worked fine. Maxwell's equations for electricity and magnetism worked fine. The only thing that you had to do is take the equations, apply them to the system that you were interested in studying, and away you go. And of note was the famous treatise by Newton called Optics, where he said, look, light must be a particle. And that kind of makes sense, because when you look at the shadow in sunlight, you have very well-defined edges to your shadow. And so that's very consistent with the picture of something that's blocking a particle or letting it through. And so it made sense. And by the way, who's going to argue with Newton? Right? Newton was the Einstein of those days. And if Newton said it, it must be true. Okay, so as of 1700, light was a particle, not a wave. But Young came along, and I've got another picture that will connect this experiment to something perhaps a little more tangible, but Young came along, 1801, and did what is now referred to as the famous Young's double slit experiment, where he demonstrated that light is a wave instead of a particle. Here he took a light source. In his case, it was just the sun. The sun is what we would call the most classical light source you can have. It's a big light source that happens in everyday life, right? So that is what we would call a classical source. You pass it through two slits. You do not see, under the right conditions, you do not see just the image of the two slits, but you see what you see in this picture here. I'm refraining from pointing with the laser pointer because I know we've got those online as well. But you can see that it's not just image of two slits, but you see bright, dark, bright, dark, bright, dark. And this is a phenomenon well known in waterways, for example. If you just take water waves and pass them through two slits, then what you see is that you get waves that emanate from the two slits. They hit a barrier on the far side, and you get spots of high water, low water, high water, low water. And that's a wave phenomenon, and that is exactly the point. That this behavior is a wave phenomenon. So that's very familiar from water waves. That could have given Young the inspiration to do it for light. If you look at this too carefully, you go a little crazy in the eyes. But the idea is, here, I'm just showing you from above exactly the same picture that you had before. The diagram on your left is just waves, water waves, sound waves, light waves, whatever, going through a single slit, and you see the source coming out. Or on the right-hand side, you have going through two slits, and you see that now we've got two sources, and they project on the far wall. Keep this picture in mind, particularly the one on the right, when we start talking about particles in two places at once. Because if I ask you, where are the waves in that second picture after the barrier, you would tell me, well, there's some over here and some over here. And you are totally okay, hopefully, with the fact that the waves are in two places at once. Okay, it's only when we get to particles that things are a little bit weird. Okay, but fine, Young showed that Newton was wrong. What else was wrong with everyday classical mechanics? And we're not going to get too detailed, but things like atomic spectra were discrete, not continuous. I will explain that in a little bit. There was something called the photoelectric effect, which I will also explain, that was showing that classical mechanics wasn't quite getting things correct. And my favorite, the ultraviolet catastrophe. That's that thing that says, oh my God, the whole space-time continuum is going to unravel, right? The ultraviolet catastrophe. I'm not sure where that name came from, but what do I mean? Okay, so let's take the sun and let's ask the question. I would like to know what is the power radiated by the sun as a function of the wavelength of light. Very simple experiment. Take solar light, pass it through a prism, measure, and you see that this is a very continuous type of spectrum. It's got some bumps and wiggles, but otherwise it's what we would call continuous. On the other hand, I could take a lamp that's filled with hydrogen, or helium, or mercury, do the same experiment, and I do not see that. I see very discrete, sharp lines, not a continuous distribution. That's telling us there's something we don't understand. What else? We had the photoelectric effect. The photoelectric effect basically says, I'm going to shine light on a metal. It causes electrons to get kicked off the metal. I can collect them, measure the current. I can measure the current as a function of frequency of light, intensity of light, whatever. I won't get into the details, but again, there was some weird behavior about it. And in fact, it was Einstein who explained the weird behavior of the photoelectric effect. It's actually very interesting to see the formula that I have written there. Ke is h nu minus be. It's a very, very simple formula. That was Einstein's contribution, and it has profound effects. So I find it amazing that such a simple equation has profound effects. Hang on 2 slides, I'll tell you what they were. What else? The ultraviolet catastrophe, that thing that will end the space-time continuum. What is that all about? Well, if I sit and I calculate, based on everyday classical mechanics, what I can expect from a radiator as a function of frequency, you see here on the left-hand side, what's labeled as the Rayleigh-Jeans law, you see that it takes off and goes up as the frequency increases. So that means that the higher the frequency of light, the more energy I need. That means I have to have an infinite radiator. Well, that doesn't make sense. When was the last time you saw an infinite energy source? Be great, but we don't have one. It turns out that Planck had to do something. He basically guessed the formula for this function that he had to fit. Don't worry about what it was in detail, but he had to guess the function, and he did. Then later he derived it. But what I find interesting is that Planck has a constant in his formula, which is an h, called Planck's constant. Okay, but it turns out that that Planck's constant was identical to the constant that Einstein put in his formula, but Einstein didn't put it in his formula. He put it in as a fitting function, essentially a fitting parameter, and when they fit their data, they found that that was also Planck's constant. So you have Planck's constant showing up in 2 different systems. That's telling us something. What is that telling us? Well, these experiments are telling us that it's pointing to quantization. Something is going on that we didn't understand before, and in particular, it's pointing to us the concept that light must be discrete particles. Okay, photons, little discrete particles of light. Okay, so a couple of things. Einstein wins the Nobel Prize for his description of the photoelectric effect. Most people on the street think he won the Nobel Prize for special relativity. He did not. It was for the explanation of the photoelectric effect, because that introduced the concept of photons and quantization of light. Okay, so now light is back to being a particle. Remember, Newton said particle, Young came along and said wave, now Einstein comes along and says, nope, back to particle. Well, which is it? Remember, we already did the Young's double slit experiment, and we saw that we don't see two images of two slits. We see wave-like behavior. So what's going on? So now we can do, and with today's technology, it's absolutely amazing. We can do the following experiment. I'm going to go ahead and do the single slit experiment again. Except this time, I'm going to send in one photon at a time. So if I think about light like a particle, the particle should pass through one slit or the other. If I think of it like a wave, it should go through like a wave, and I should see interference. And so the question becomes, what do I see? So here in this image, you see little bright specks appearing. That's because this is a single photon sensitive camera, and you are seeing single photons striking the screen. And we're doing this over and over and over again. And so you say, aha, Einstein must have been right, Newton must have been right, it's a particle, because I see particle-like behavior as these photons are striking the screen. But if you look long enough, which is kind of about now, it looks better on my computer, you can kind of see it on the screen, and you can definitely see it on the plot below. I don't see two slits, I see the wave interference. And so it is absolutely remarkable that even though I do the experiment one photon at a time, there's no possibility that photons are somehow interfering with each other. It's one photon that has gone through this double slit showing interference. So that means that the particle must be in a superposition of having gone through the left and gone through the right at the same time. Okay, I didn't say or. I said and. The particle went through the left and the right. And it's only when I go at the end to look at the measurement that I see interference. Okay, so I use the word superposition. So let's talk about what does superposition mean. Okay, let's go back to the classical world. I have an object, and I say the object is blue. And I have another object, and I say it's red. And now I'm going to somehow combine these two systems together. When we combine these two systems together, we say, well, this system is now somehow an average, a mixture of these two systems. And so we say it's green, because green is somehow the average of blue and red. Hopefully I got those colors right. Okay, but in the quantum world, the thinking is fundamentally different. The thinking is this: I'm going to take a system, and the system is blue, and another system, and the system is red, and I'm going to create a superposition of those two systems. It is not a green system. In quantum mechanics, it behaves like it's blue sometimes, and it behaves like it's red sometimes. What makes it decide? Einstein's famous quote, God rolls the dice, and that's how you decide. More on that topic later. But think about a coin, right? Heads or tails. Okay, if I spin the coin, by the way, this is one of these analogies, you push too far, it breaks down. If I spin the coin, okay, and I can't spin this because it's not the right shape, but if I spin this, I can think of this as my analogy to a superposition. As it's spinning, it's both heads or tails. It's only when I smack it down that I say, aha, it's heads. Now, in the classical world, if I measure the speed very carefully and I measure the tilt very carefully and my hands very carefully, I can predict whether I'm going to get heads or tails. In the quantum world, it's not. You cannot predict. It's legitimately both heads or tails until you make a measurement. So that seems a little weird. By the way, the terminology is collapse. We collapse the wave function. All that means is it says we make a measurement. Slap the coin down. Do we get heads or tails? More on that in a little bit as well. But this means that now I can say, okay, now I'm starting to maybe understand a little bit about this wave-like property. Okay, maybe I can have a wave like what's depicted on the top here, very spread out, and I can have a detector that's supposed to go click whenever it finds a particle, and I will see some wave behavior. There'll be places where the detector goes click more often than not, or as in the case of the second one, where I have a very, very localized wave, I can get maybe just a few clicks where it's very localized. But the point that I want to make here now is that quantum mechanics can only give us probability of events. It cannot tell us what an event is going to happen. Okay, let me give you the following analogy again. Okay, so I'm going to take a tennis ball. Fortunately, I didn't bring it because I don't want to club anybody with it. All right, and if I do the following experiment, I'm going to spin around 3, 4, 5 times, it doesn't matter what. My eyes are going to be closed, and I'm going to throw the ball after a few spins. All right, now, as I'm spinning, I might think I'm facing this way, but maybe I'm facing that way. Maybe I'm facing that way, so there's a probability I'm going to shoot somewhere. Again, in the classical world, I could, in principle, actually calculate it, but we're going to skip that part. In the quantum world now, there's a probability. Okay, now here's where it gets a little wacky. Okay, so fasten your seatbelts. Okay, so now I'm going to take the ball, and I'm going to throw it, and Scott catches the ball. Okay, now that's a given. He caught the ball. Okay, so we know the ball went that way. Well, Einstein asked the following question. I hope that's my next slide. Yes. Okay, so Scott has caught the ball. Where was the ball the second before he caught it? That's a question for the audience to ponder for a second. Who wants to be brave enough and answer that question? Douglas, you're right there.
Well, as a former baseball player, I would say it was just beyond his outstretched hand.
Just beyond his outstretched hand. And you would be in excellent company. Okay? You happen to agree with Al. Okay? Al said, well, that's, actually, he said, that's a really dumb question, right? Given that the ball was caught over here, where else would the ball have been a second before he caught it? It has to have been right before it. The problem with quantum mechanics is that quantum mechanics cannot tell me that ahead of time. It can only tell me the probability that it's over there, but once you've detected it, then the ball must have been right in front. It's just that quantum mechanics isn't complete. There's something not 100% complete is really the word I'm looking for, right? There is a hidden variable in play. I will talk a little bit more about hidden variables in just a second. Okay, so we've got Einstein and Douglas who say right in front of Scott's hand. Who's going to argue with Einstein or Douglas? Right? Well, another heavy hitter steps in. Niels Bohr. Niels Bohr said, "Nah, Einstein, you're wrong. The ball, the tennis ball, the wave, the particle, the photon, whatever it is, right before the detector, even though the detector has gone click, even though I know the ball went there, not over there, the second before the detection, it was still everywhere. It was the measurement that localized it to there. And that's induced the collapse of the wave function. Okay, so we've got Einstein and Bohr who are debating this. Okay, so let me tell you a little bit about this hidden variable and what's called hidden variable theory that Einstein is talking about. Basically, this is just the idea that a particle has a property unknown to the experimenter and unknowable to the experimenter that causes the particle to go over here and not over there. So there's something inside that's going to do this. The photon has a hidden property. It also, there's also the term realistic, we're going to talk about reality in just a second, that says the property of the particle is determined. So Einstein is saying, look, we can only describe probability, but given that the ball has gone over there, that particular instance of photon has to have had a property as it left my hand that I don't know about but caused it to go that direction. Okay, so what's a hidden variable? Very simple. Okay, every optics person, every experimentalist optics knows about these. That's where we get all our lab snacks from. Okay, and all I've done, really high tech. Okay, got an orange card over here, and I've got a red, blue, I'm not colorblind, blue card here. Okay, so you gotta pay attention now, right? Red and blue. Okay, and now we do one of these. Which one has the blue? Okay, let me clarify. This is not a magic act. This is quantum mechanics. Right? If this is a magic act, out would come a dove or something. But yes, that's exactly right. Okay, but now we're going to do the same experiment. Okay, same experiment, slightly different. Here's the blue card, just for kicks. Here's the red card, just for kicks. And what am I going to do this time? Okay, which one has the blue card? Are you willing to bet the house on it? Yes or no?
Am I what?
Would you be willing to bet your house?
Oh,
The stakes are a little higher now.
what did they both have blue cards?
They both have blue cards. That's an interesting observation. Who agrees with that one? Justin agrees with that one. All right. Well, here's a blue card. So you're halfway there. But here's the other one.
So you measured it.
I did measure it. Let me ask the following question. Let me just redirect slightly. That's exactly right. You're on the right track. But here's the thing, right? He said, it's in the right one. But as soon as I said, are you willing to bet the house? He's like, maybe not, right? What was different about that experiment? The first one, everybody said, yep, it's over here. What about this experiment? What was different? Hidden. There was something hidden, right, that caused you to say, well, we don't know what's going on. That's all hidden variable is saying that the particle has something hidden that the experimenter does not know about and can't know about. Okay, and so that's the problem. So now we're back to this question. Where was the particle right before? Here's another question, though. How do we test that theory? Right? It sounds like a dumb question, first of all, right? If I throw and the ball is over there, just before it, it has to have been just before the hand. But how do you test that? Well, you make a measurement right before his hand. Yeah, but now you've made a measurement. Oh, so we put the detector right... No, now you've made another measurement. Okay, how do we test this? And so the question is, I don't know, how do we tell? So this was debated for a long time. If I remember correctly, but don't quote me on this, I believe the debate started somewhere in the 20s, maybe, give or take. And so, how do we resolve this? Right? What's the reality here? And so, we're going to bring in entanglement. Now, finally, we can talk about entanglement. What is entanglement? Don't read the words, I stole it from Wikipedia. You can go read it yourself. But the idea is, I'm going to now talk about two systems, two particles, two photons, that cannot be described by the individual properties of the individual photons. What does that mean? Let's go back to our coin example. Okay? Back to our coin example. Now I've got two coins. Heads and tails, Those of you who don't believe me, you can come and check out afterwards, right? And this is our model of spinning coins. Okay, so how would I describe what a coin does? Well, I'm going to toss this coin now 1,000 times. Okay, well that would be really boring for you to watch me do it 1,000 times, so we're not going to do that. What we're going to do is we're going to have the computer do it for me. So what would you expect if I flip a coin 1,000 times? Okay, well here we're flipping the coins and I'm counting the number of times I get heads and the number of times I get tails. After 1,000 tosses, you see that pretty close I get 50-50. That's exactly what you would expect with an experimental error. Nothing fancy there. Okay, now we're going to do the same exact experiment with 2 coins. Okay, so I'm now going to flip both coins and record the results, and I'm going to bin them heads, tails, 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 heads, and heads, heads, whichever one I forgot. Okay, so we're going to do that experiment. Okay, and after 1,000 or so tosses, right about there, you find that, yeah, within experimental error, we get about 250 apiece, so all is fair. Okay, now I'm going to do another experiment. I'm going to do something different to the coins, I'm not going to tell you what, and we're going to run this experiment again. Okay, so I run the experiment again, and this time you notice something very interesting. I either get heads, tails, or tails, heads. I never get heads, heads, or tails, tails. Okay, so what experiment am I doing? I'm doing the following experiment. I've got my coins over here, and all the way over here I've got my other set of coins. And you can pretend that these are, a couple of light years apart. Okay, and so now I'm doing the measurements. Okay, slapping that one down, measure head, slapping that one down, that's tails. Okay, doing this over and over again. Somehow, that coin is saying to that coin, hey, I'm heads, you have to be tails. Or, this time I decide to be tails, so you have to be heads. Okay, and these particles can be separated by light years, but this weird property that I stuck on these coins still works. This is the concept of Einstein's spooky action at a distance. Somehow, these coins, which I separated by a lot, why? Because I don't want them to be able to communicate at the speed of light. I need them to be outside the communication range so that they can't talk to each other. Then we find that this is what's called entanglement. Somehow, there's a property of these particles that causes that one and that one to always be opposite. Important to note for later on, if I take that table and tilt it at 45 degrees, so I'm measuring in a different reference frame, so somehow heads is now on a tilt, these particles are still going to be entangled. If I tilt that one and I tilt that one, this will always be heads, and that one tails in this tilted frame, or that one's tails and this one's head in the tilted frame. Okay, so now we get into the weird world here. So this Einstein-Bohr dilemma was debated for a long time. How to resolve this? Without making a measurement, how can you tell what the measurement has done? Then an Irish physicist named John Bell came up with his seminal paper in 1964 that answered that question, providing testable experiments that could be done with entanglement. And I'm not going to go through the whole nitty-gritty detail, but the idea is basically, let's take an entangler, something that causes this system of spooky action at a distance particles. What we're going to do is we're going to do a whole series of measurements. Some with this one inclined at some angle, this one inclined at some angle, and I'm going to make a whole bunch of measurements of heads, tails, etc., and calculate some type of correlation functions. Doesn't matter what we calculate, but this picture is beautiful. You can't see it particularly well in this classroom, but John Bell is at the chalkboard, and he's got this expression, and it says less than or equal to 2, or less than or equal to 2 root 2. So the idea is basically the following. I now have a measurement that I can do with these entanglers and collect them, process them. If I get an answer less than 2, then that means Einstein was correct, and there's a hidden variable, and that all sits very well with us, because then that kind of makes us feel better. Or, if I get a result that's close to 2 root 2, then that means Bohr is correct. When these gentlemen pictured here, Alain Aspect and John Clauser, did the first measurements. Here what I've drawn is a picture through some of their data, or a line through some of their data. The idea is I do this entangling experiment with these bases that are flipping around, and I should be able to go smoothly from one orientation to the other in a straight line collecting this data. And you see that John Clauser's data on the left is not a straight line. It is very much not a straight line. And in fact, Bell's theory says you get maximum violation of this line, maximum deviation away from this line that says Einstein is correct and Bohr is wrong, at 22.5 degrees or 67.5 degrees. Okay? And Aspect did a similar experiment about 10 years later, however, very much not a Me Too type of experiment where he closed a bunch of loopholes and other arguments there. But we very clearly can see the data is not a straight line. What does this mean? What is the bottom line? Oh yeah, by the way, here in Aspect's paper, he says, look, our quantity that we're looking for, that parameter that I said you collect and calculate, should be less than 2 if Einstein is correct, or bigger than 2 if Bohr is correct. He got 2.7, plus or minus 0.05. Very, very clear violation of Bell's inequalities. That's exactly what they've done. And they've now shown quantum mechanics. Great story, by the way. John Clauser supposedly went running into Richard Feynman's office, another Nobel laureate, saying, hey, look at this wonderful data, quantum mechanics is right. And Feynman said, well, of course it's right. Stop wasting your time and get back to work. This was just a beautiful, beautiful result. And by the way, look at the data points. The error bars on these data points are smaller than the points themselves. So it's just absolutely impressive data. But what does this mean? By the way, I encourage you to check out the Nobel lectures posted on these YouTube links here. Alain Aspect in particular, I haven't listened to the Clauser one yet. Alain Aspect is a fabulous speaker, and he can explain some of this stuff way better than I can. Okay, so where are we at this point? That means Bohr was correct. That means that the ball that went over there and was caught, the fraction of a second before it was caught, it was not there. It was still somewhere here. And any particle does not have a property that you're going to measure until you measure it. It's not predetermined. These blue and red cards, as I put them in the boxes, are not blue and red and you just don't know it. They are blue and red until you make the measurement. It is completely counterintuitive, but that's it. So the particle is everywhere until you measure it. The properties of the particles don't even exist until you measure it. And the act of measuring and the collapse of the waveform is all correct. Okay, so since I'm running out of time a little bit, let me just, last point here. In the language of quantum mechanics, we have locality, two objects that are separated by a distance further than the speed of light and some time cannot influence each other. That's locality. Realism is the statement that says all particles have properties that are defined. The results of the Nobel lecturer experiments tell us we have to throw out the concept of reality, okay, that particles have properties before we measure them, or locality, that particles outside a light tone can't talk to each other, or both. Okay, and that's just the way it is. If you don't like it, I am sorry. That is quantum mechanics. Okay, so what is this all useful for? Where can I use this in, I don't want to say everyday life, but it is every day for me. I will definitely say that. So here's kind of an outline of some things that you might be able to do with these results. You can make inertial sensors. You can have quantum secure communications, encryption, teleportation, and quantum computers. And I will hit those very quickly in the last few minutes that I've got. Just to quickly tell you about atom interferometers, which is my livelihood. This is what I do every day. De Broglie came along in 1924. PhD thesis, talk about an impressive PhD thesis. It's extremely small, it's only like 70 pages long. And he basically said, hey, look, if a photon is allowed to be a wave and a particle, well, then a particle should be allowed to be a particle and a wave. So things like electrons and neutrons and atoms should all behave like waves. Wouldn't that be kind of a cool? And he was exactly right, because in 1930 they demonstrated electron diffraction, which is a wave property. So particles are now behaving like waves. So we can now go and do a double slit experiment, except this time instead of using photons, I can use atoms instead. And so now we do exactly the same experiment, and look, we see interference in which way atoms went through a double slit experiment. Okay, so atoms that we are now all of us in this room, I can guarantee you, stop and we think about atoms that look like spheres, particles, right? That's the way we're used to thinking about them, but they're not. They can be made to behave like waves, and by the way, I will unabashedly tell you, that's data from my lab. This is what we do every day. So we are making atoms behave like waves. Why would we want to do something like that? There's my plug, those are atoms. Why would we want to do something like that? Because they're atoms and they're not photons. They are sensitive to things like gravity, rotation, magnetic fields. I have probably forgot one or two. But they are very sensitive. How much more sensitive? 10 orders of magnitude more sensitive. I can make, in theory, a gyroscope, something to measure spinning, that is not a factor of 10, a factor of 10 to the 10. 10 billion times more sensitive than an otherwise equal interferometer. Now, I was very careful to say otherwise equal. You have to take off a few correction factors, blah, 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 but you're still 4 orders of magnitude better. Easily. And that's exactly what we find. So with state-of-the-art sensors that are being developed now, if you break them open and look into the heart of them, you find atom interferometers for gravimeters, gravity gradiometers, gyroscopes, atomic clocks, and magnetometers. Useful for these applications. No entanglement in these yet, but if you do put entanglement, in fact I was just having a conversation with my colleague earlier this afternoon, if we were able to put entanglement, that would be great. Nobody in the field knows how to do that yet, but that's okay. What about quantum communication? We can have what's called quantum secure communication, quantum key distribution. This is a technique using photons, using entanglement, in which you can communicate protected by the laws of quantum mechanics, not by anything else. So this was first put forth by Bennett and Broussard. One of the first protocols was by these two gentlemen. That's why the protocol is called BB84, published in 1984. And then there was an improved method, and there have been all sorts of protocols that have come out after that. Basic idea goes back to, I'm going to use entanglement for this particular description, right? Remember, I've got entanglement where this guy is either heads or tails, but if he's heads, she's tail, and if he's tail, she's heads, right? But I can mix how I measure. So what we can do is the following experiment. We're going to do 100 of these realizations where Alice is going to scramble what basis she measures. The flat basis or the tilted basis. Bob over here, do the same thing. On average, half the time, they're going to measure the same, in the same basis, both flat or both tilted. Completely by random, completely by chance. They flip however they feel like it. But remember, these particles are entangled. Heads up over here has to be tails over here, and vice versa. So now, Alice and Bob, when they're done making the measurements, can get on an open channel. They can call on their cell phones, email, unencrypted email, doesn't matter. And what they share is not the results of their measurements, but just what basis they measured in. That's it. Because as soon as they specify which basis, and they agree, they know what the result of each other's measurements were. And they can use that to form the basis of a one-time encryption pact. What about an eavesdropper? What happens with an eavesdropper? Well, what does the eavesdropper have to do? The eavesdropper has to grab a photon, okay, Alice has her photon over there, she sends one over here to Bob. She has to grab that photon from Bob, but Bob's going to notice a missing photon, so she has to send another one to Bob in place. But she's going to have to guess how Bob is going to make a measurement and send a photon based on her guess. So she's going to make a mistake 25% of the time. If Alice and Bob have a decent communication system that has an error rate less than 25%, which is trivial to do, that's easy, all of a sudden your error rate goes up to 25%, and you say, aha, Alice and Bob will say, we must have an eavesdropper, stop communication, but the beauty of it is you haven't sent anything that can't be intercepted. Okay, you have not sent any information, you've only sent some kind of secure pad. In fact, you haven't even sent that, you've sent the basis for it. So you have discovered the presence of an eavesdropper, and you have not revealed any of your information, protected by the laws of quantum mechanics. What about teleportation? This one is cool, right? Because when you think about teleportation, I'm a Trekkie, I admit it. Okay, so here's one from the next generation, right? Beam me up. What do we think of when we think of teleportation? Well, we think of, poor James Kirk. He's stuck on a planet somewhere, he's got to get off. How do you get off the planet? Well, you just call for a transporter, right? He just gets transported up to the Enterprise. Well, in quantum teleportation, that is almost exactly what we're doing. Okay? So here is a picture where we've got some kind of entangler. Alice has, as depicted on the left-hand side, labeled A1, some state of a photon or state of an atom that she wants to transmit to Bob. Okay, well, she can't measure it because in the process of measuring it, she's going to destroy it. So what she's going to do is she's going to measure that and one particle of this entangled source that she shares with Bob. And as a result of those measurements, she's going to tell Bob what to do. Bob is not going to make a measurement because if he measures his photon, he's destroyed it. What he's going to do are some operations on it, some manipulations. When he's done the manipulations as described to him by Alice, based on her measurements, when all is said and done, Bob will now have a copy of the state that Alice started with. So Alice has teleported the state over. Okay, lastly, quantum computers. Who here thinks that quantum computers is going to be like the world's most ultimate gaming machine? Right? This is just blazing fast, right? Not quite. I'll get to that in just a second. But where does the power of a quantum computer come from? Okay, so we're not going to get too deep into theory, but everybody knows about a classical bit, a 0 or a 1. And a computer stores information only on the basis of zeros and ones. So, for example, I want to store the number 2 in a 3-bit register, like I have depicted here next to the classical computer. So I write 0, 1, 0. That's the number 2 in binary. Takes 3 bits, and that's the only information that classical computer can store, the number 2. That's it. If I wanted to store another number, I need 3 more bits. A quantum computer, because of this concept of superposition, I can use 3 qubits, and I can store all 8 numbers in one 3-bit qubit. So I can use now, superposition to help me make a computer that is basically massively parallel processing. I can do all the computations simultaneously rather than in the classical computer, one bit at a time. That's kind of the bottom line. These seem like fantastic numbers that I'm about to tell you about, but there's a reference there, so I lean on the reference. Okay, but here's something that you can contemplate. If I want to factor a 500-digit number, factoring is a hard math step, right? When we teach factoring, how do we teach it? Well, you try the number 2, you try the number 3, you try the number, and you get a little bit of sophistication, but not much. It's a hard problem. So factoring 500 digits on a 2.2 gigahertz classical processor will take you 10 to the 12 years. I'm not waiting that long. I might, actually, I could. Right? On a quantum computer with the right hardware, in principle, you could do it in 2 seconds because of this massive parallel processing that you can get because you can store way more information on qubits than you can in classical bits. So, anybody ready to break out their checkbook and buy one? That would be cool if we could do that. Well, you can. Okay, you can buy something called the D-Wave machine, for example. It is literally a black box. Okay, it is 700 cubic feet, and it is all cryogenic coolers. The guts of the machine is about 1 millimeter square. It's a chip that occurs at the very, very bottom of a cryostat that reaches a temperature of 15 millikelvin. By my standards, quite hot, but yes, I did say hot. That can be for the questions, that's a C question there. But you've got to get your temperatures down to 15 millikelvin. But one can certainly envision that maybe this is exactly the way our classical computers started. Here's a picture of the ENIAC, first computer built. All it could do was add and subtract. This little device has way more computing power than that does. But, not a bad beginning. So yes, you might be able to buy one, $15 million right now with a $3 million per year service contract. Piece of cake, right? Okay, where else can you get a quantum computer? All the typical players, by the way, the D-Wave does not use entanglement. It just doesn't. Other computers other companies that are working on quantum computers, they allow interfacing, but I don't believe you can buy one. I'm not 100% sure of that statement, but they do use entanglement. Key takeaway from this slide here is that, for the moment, to the best of my knowledge, quantum computers are only good for certain problems. They are not going to be a super wonderful gaming machine. They're not going to be super wonderful, surf the internet super fast. Okay, it is only good for solving specific problems. Like what? Glad you asked. Like the traveling salesman problem. Okay, very famous, how you hit most cities in the least amount of time. Or finding the factors of a very large number. If I ask a classical computer to factor that number, the computer's going to go up in smoke. Okay, but a quantum computer can do it. So those types of problems. So, to recap what we've talked about today, I gave you a little bit of a history lesson in how quantum mechanics came about, the revolution that was quantum mechanics. I hopefully gave you a flavor of this wacky world. My computer just died over there, I guess time's up. Little bit of flavor of what the wacky world of quantum mechanics is and what it can possibly be good for. And I believe that is my last slide. Thank you very much for your attention for this opportunity.
Thank you, Professor. Why don't you just take your own questions as folks ask. And let's ask some questions.
So the question is, okay, you talked about entanglement and entangled particles. Are they correlated and how do you do that? And so the answer is they are very much correlated because the second I detect that the particle over here is a heads, like a coin, then its tails over there. However, if you were to go home and take 2 coins and start flipping them, they're not going to be entangled. There's something that I have to do. With coins, I have absolutely no idea how to entangle 2 coins. But there are processes in optics where we can do exactly that. I can entangle photons. I can put a property known as polarization of the photons and say, well, if this photon has polarization up, this one must have polarization horizontal and vice versa. That we can do. So yes, there are things we can do to entangle, and that was actually the whole point of the Clauser and Aspect experiments. They made an entangler and were able to test Bell's theories. That is your question?
Yeah.
So if quantum mechanics is probabilistic, the Schrödinger wave is deterministic. How do you balance? I get confused with that. Is it deterministic, probabilistic?
I wonder why you were saying the Schrödinger equation is deterministic.
Because that's what Adam Becker says in his history of quantum mechanics.
So I would say that the Schrödinger equation is a tool that we can use to do some calculations. In the end, what do you calculate? You calculate a wave amplitude, and you square it and get a probability. That's the way I think of the Schrödinger equation. It's a tool to calculate the probabilities, but it's always a probability. I can never determine anything 100%, not deterministic. That answer your question satisfactorily?
I'm thinking of the EPR paper.
Okay. Okay, so the question is, he's thinking about the EPR paper, the Einstein-Podolsky-Rosen paper, that is exactly what spun off this whole Einstein-Bohr debate. And so I'm not sure what you're thinking about in that context, but that was a system that explored this incompleteness of quantum mechanics and that whole description and that whole, well, there must be a hidden variable. And then Bell said, nope, hidden variable theory is out the door, and that's been experimentally demonstrated. That's the message you got to take away. It's been experimentally demonstrated that hidden variables cannot explain what we think of as reality.
Do you think that your ideas still stay the same if you, instead of saying it collapses when you measure, you say it collapses when there's an interaction? In other words, the difference is measurement, you have a human observer. Interaction, not necessarily.
Okay, so the question is, basically, does the entire premise of this talk change if I change the word measurement to interaction? That's a really good question. I don't know that I'm going to come up with a very good answer. So what I'm thinking about is there is the possibility, I guess, of something called like non-demolition measurements, somewhere I can get some information out without destroying a particle. I don't know that I've got a great answer for your question. Beautiful question, don't have an answer.
Mine is less theoretical. Could you describe a little bit in practical terms how quantum sensing will affect anti-submarine?
Sure. Okay, so the question is, how can quantum sensing affect anti-submarine warfare? So, very nuts and bolts. What is one of the major problems of detecting a submarine? We can do sonar, and we get some idea, but we now need to localize. How do you localize? You bring a magnetometer in to detect the magnetic signature of a submarine, right? Submarine is chunk of metal behaves like a magnet. How do you detect a magnet with another magnet? That's basically the way it works. But the magnetometer is often swamped by noise. All right, you've got ionosphere activity, solar flares, magnetic earth, blah, 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 blah. And so you cannot detect the presence of the submarine with the magnetometer, largely because of the noise. So it's akin to trying to talk to your buddy, like my buddy Drago all the way in the corner there, in a noisy room. If everybody started here talking, I can't have a conversation with him. If I throw my hearing aid, it doesn't help, right? But with a quantum sensor, you might be able to get rid of some of that clutter, either by, more sensitive is one possibility, but gradient detection is another, things like that. Or looking for signatures like a gravity signature, something like that.
What are the theories about what that
forces or the communication between two particles that are entangled. I mean, there's something there. There's some.
So what is this spooky action at a distance
Right.
mechanism? It's quantum mechanics. It's the property, yeah, so it's, the problem is that in our everyday life, where's my other thing? Right? The problem is in our everyday life, we tend to think about, okay, I have a coin here, and I have a coin here, and I'm going to explain the system of coins as something about this and something about that. That's the wrong way to think about entanglement. I have a system. So it's not that there's a system over here and a system over here and they're talking to each other. That's the system. That's the way I think about it. So there's no need for a force or line of communication between the two because it's all one thing. It's not two objects. I don't know if that helped or was satisfying, but that's the wackiness of quantum
We'll
mechanics.
take one last question.
So I was actually thinking of something very similar. Because it's one system, it's not two different things interacting, together. It's one system, so I was thinking in terms of memory. It has the same memory. So if one part of the system is tilting or going to be heads, then the other part of the system will know that it has to be the other way because it shares the same memory, is kind of the way I was thinking about it.
You can kind of think of that. You run into trouble. Okay, so the question is, right, isn't there basically some kind of memory that if the particle over here has to be heads, then memory of this system says that this one has to be tails. And you can think of it that way. The only trouble that you run into is you have to remember over here, if I don't care about that particle, and I look at just this one and measure over and over and over and over again, sometimes I'll have heads, sometimes I'll have tails, sometimes I have heads, sometimes I have tails. Completely random. It's when you look at the two together that you find this entanglement of always being opposite. So it's not so much a memory thing because this particle here didn't know it was going to be heads or didn't know it was going to be tails until it made the measurement.
Well, you didn't know, as the person.
No. That's the beauty of, that's, you are in great company. That's what Einstein said. There's a hidden variable in play here. The Bell inequality experiments said no, wrong way to think about it. That the concept of heads or tails, and I just don't know, out the window. It's heads and tails, until you make the measurement. So, sorry to tell you you're wrong, but you're a great company.
That's okay, but I understand the concept of being both at the same time. It's at the measurement where you see it.
The measurement causes the collapse and immediately causes a collapse on the other side as well.
All right, so we can collapse on the snacks that are on the counters. And please join me in thanking Dr. Professor Chairman Narducci.